Hi class, in this video what I want to do is I want to talk about something called independence and the multiplication rule. And what this is going to do is this is going to allow us to answer some of the harder problems that come up this week. Okay, so for this lecture I have two objectives I want to get through with you. I want to talk about independent events and I want to talk about the use of the multiplication rule for independent events. So first off, what the heck are independent events, or how do you identify them? Okay, so let me give you the definition and we'll work some examples of this. So two events, we'll just call them E and F, okay, those are two things that happen in probability, are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. So what I'm saying here is if you have two events, what happens first will not change the outcome or not have an impact on the outcome of what comes second. Two events are dependent then if the occurrence of event E in a probability experiment does affect the occurrence of probability F. So what happens first, if it does impact or change the probability that what happens next, that those two events would be dependent. So we're going to focus on independent events in this lecture. All right, so let me give you three examples here, and then I want to ask if they're independent or not, and then we'll work through them. Okay, suppose you draw a card from a standard 52 card deck of cards and then you roll a die. So we have two events. We have drawing a card and then rolling. The two events we're looking at here, are that you draw a heart from the deck and that you roll. The second thing is that you roll an even number. Now these two events are independent because if I draw a heart from the deck, it doesn't change the probability that I would then roll an even number. Okay, so they are independent because the results of choosing a card does not impact the result of a die roll. Obviously, that makes sense. All right, so next, suppose two 40-year-old women who live in the United States are randomly selected. The events woman 1 survives a year and woman 2 survives a year. Because you're sampling from or pulling people at random from a really, really large population, the probability that the first woman survives is not going to affect or change the probability that the second woman survives. So they're independent. So when you sample from a really large population, doesn't matter. Now suppose it's instead from a small population. So suppose two 40-year-old women live in the same apartment complex. The event woman 1 survives the year and woman 2 survives the year. These are dependent, okay, because the probability, once you take one woman out of the apartment complex, it's really going to change the probability that you select another woman from the same complex. It'll alter it just enough. So those are dependent. So we're going to work at the first two type of problems, A and B. All right, so now we have this thing called the multiplication rule for independent events. And it just goes like this. If E and F are independent events, then if I ask you the probability that E and F happens, all you have to do is take the probability of the first event, multiply it by the probability of the second event, and that's it. Okay, so whenever you see this and statement in here, it just implies multiplication. All right, so let me give you an example. The probability that a randomly selected female aged 60 years old will survive the year, okay, so a female will make it from 60 to 61, is 99.186%. And this is according to the National Vital Statistics Report. So what is the probability that two randomly selected 60-year-old females will survive the year? Well, we know the survival of the first female is independent of the survival of the second female, okay, because they're just people at randomly selected from a large population. So we also know then that the probability that somebody survives is 0.99186. So just changing this to a decimal. So the way we would write this is we'd say it's the probability the first woman survives and the second woman survives. Well, because they're independent, and I'm going to go back, E and F, you just take the probability of the first event, multiply it by the probability of the second event. So it's the probability the first woman survives times the probability the second woman survives. Well, the probability they survive is each 0.99186. So it's just 0.99186 times itself, or squared, which gets you 0.9838, just like that. All right, let's try another one. A manufacturer of exercise equipment also knows that 10% of the products that come out of the assembly line that are made are defective. They also know that only 30% of their customers will actually use the equipment in the first year it is purchased. Interesting. If there is a 1-year warranty on the equipment, what proportion of customers will actually make a valid warranty claim? Well, so we assume that defectiveness of the equipment is independent of equipment use. Seems reasonable to assume. So I need to find the probability that it's defective and they use it so that they know it's defective and get their 1-year warranty. Well, since we just said they're independent of each other, it's the probability that it's defective, which we know is 10%, times the probability it's used, which is only 30%. So that's 0.10 times 0.30. Well, when you multiply that, there's only a 3% chance that they will use that 1-year warranty. All right, you can expand this, all right, instead of just 2 events. So if events E1, E2, E3, all the way to En could be 4, it could be 100 independent events, as long as they're independent. If I ask you the probability that they all happen, E1 and E2 and E3 happens, and all the way to E sub n happens, that's just equal to the probability of the first one times probability of the second one, all the way to the probability of the last one happening. So let me give you just an example on this one. So the probability that a randomly selected female aged 60 years old will survive the year is, again, 99.186%. This is according to the National Vital Statistics Report. What is the probability that 4 randomly selected 60-year-old females will survive the year? All right, so it's the probability all 4 survive. Well, so this is the probability that the first survives, and at the same time the second survives, and the third survives, and the fourth survives. Well, since we're sampling from or taking randomly selected from a large population, these are all independent. So we're just going to multiply the probability of each 4 times. So we know the probability they survive is 0.99186, so it's 0.99186 times itself 4 times. And that just gets me 0.9678. And that's our answer right there. All right, I hope that helped and the examples were useful for you.